Professor Xiaoyi Liu. He is assistant professor in the Department of Computer Science and Engineering at the University of California. His current research interests include high-performance interconnects, advanced I/O technologies, big data analytics, parallel computing, virtualization, cloud computing, all the topics relevant to our audience here. He has published more than 100 papers in major international conferences, workshops, and journals, and he's also gotten Best Student Award or nominations. So I'm excited to have him present to our OFA audience, and he should be able to share his screen and start talking. And any questions, please feel free, guys, to bring it up during the talk via chat, or if there is 5 to 10 minutes, which we usually reserve during the end of the presentation, you can also verbally ask your questions.
Okay, thank you. Okay, sure. Thanks a lot for the introduction. So this is Xiaoyi from University of California, Merced. So today I'm very glad to present our recent work called INEC, which means in-network erasure coding. So as we all know, right, we are in the era of data exploration. Next slide, please. So data is growing and will keep growing rapidly. As the red solid line show here in the figure, the annual data size is increasing superlinearly, and it is expected to be around 175 zettabytes by 2025. In the meantime, if you look at the costs of different types of drives, like a hard disk drive or solid state drives, we see that their cost is decreasing. That's good. The problem is the price of these drives actually is decreasing linearly. The total storage cost for storing all data, which is growing superlinearly, means that in the end, we surprisingly to see that we need to spend a lot of money on the increased cost to purchase different type of drives, right? So in this case, we can say that storage devices is no longer a cheap resources these days for data centers, clusters, or HPC clusters. So this fact in turn forces us to rethink about how to design next generation distributed or disaggregated storage systems. Next slide, please. So typically in a distributed storage system, we can choose not to use any fault tolerance mechanism to keep the storage overhead as lowest as possible, right? But in that case, the system is not reliable, which is not a good way to keep our data, right? Because at some point, we will likely lose some data. To achieve reliability, the many widely used distributed storage systems adopt n-way replication. This is very simple and easy to implement. That means the system will store n replicas for any piece of data to tolerate up to n-1 node failures. However, as shown in this figure, the use of replication will cause performance degradation and, of course, significantly increase the storage overhead because you have to store each piece of data by n times, right? So now the question is if there are any alternative approaches in between to reduce the storage overhead. The answer is yes. So erasure coding is a standard alternative approach to achieve storage efficient reliability solution for distributed storage systems. Next slide, please. So in order to introduce our work clearly, let's briefly just overview some easy basic concepts, especially we take the Reed-Solomon code, for example. So maybe next slide, please. Maybe many of you already know EC, but some of you who don't know EC well, please just go over with me in about 3 slides. Let me briefly, quickly introduce how Reed-Solomon code works, and then you can also think similar approaches can be applied to other codes, which can provide you reliability for your storage media as well. So Reed-Solomon code is a very famous and widely used erasure code for storage systems. It has 2 essential parameters. One is K, the other one is N. So we usually use RSK, N to represent the Solomon code. So with the configuration of K and N, of course, you can choose different K and different N, right? Different values of K and N. The coder will generate N parity chunks and for K data chunks, as shown in this figure. And it is able to recover the original data on any K survived chunks when data corruption occurs. Now let's see the example showing this slice. This is show the case of k equals to 4 and m equals to 2. So for encoding, the coder just use a predefined invertible generator matrix to multiply with 4 data chunks, and then the result will consist of 4 data chunks and 2 parity chunks as shown in the figure. Okay, the data chunks and the parity chunks. One row means 1 chunk. So next slide, please. So after encoding, this data and the parity chunks are distributed across different nodes. So let's say these 6 rows can be distributed to 6 nodes. Okay. So now suppose 2 data chunks are corrupted. So then if we also cancel out the 2 corresponding rows in this generator matrix, and then this equation still satisfies, right? So next slide, please. Now, if you want to recover the data, right? So now this means the survive, we need to use some approach to get original data from the survive data. Earlier, we have 2 rows get removed. So if we multiply the inverse matrix of the remaining generator matrix on both sides, and then the inverse matrix and the remaining generator matrix on the left side will be canceled out because they will become an identity matrix, right? So then only the original data chunks are there. And that's why the left side just becomes to original data matrix. So therefore, we finally get the original data chunks from the survived chunks, right? Essentially means survived data just needs to multiply with the inverse matrix again, so you'll get the original data easily. So this is the key idea of data recovery for reinforcement code. Similar approach can be applied for other Erasure coding schemes as well, or codes as well. So if you look at this reinforcement code, the most beautiful feature of reinforcement code or other Erasure coding is that it can provide you very good storage efficiency, or while it also maintain the similar or same level of reliability compared with n-way replication. For instance, if you choose RS4,2, you only need to spend 1.5x overhead to achieve same level of reliability as 3-way replication. So which 3 replication, you need 3 times storage overhead, right? So you save almost half of the storage spaces, which means you save a lot of money. Similarly, you can use RS6,3 to achieve similar kind of storage efficiency compared with 4-way replication. So next slide, please. Now the question is, let's see how we take a quick look how EC works in write and read pipelines in the real distributed storage system. So for write, whenever the client get enough data chunks, you have to perform encode on them and then generate the parity chunks, like we said in the earlier slides, and then send them out to the data nodes. Right here is 3,2, so you need to send to 3. You need to send 3 data chunks, like a blue box shows, to 3 data nodes, and then 2 parity chunks to another 2 parity nodes, which show in the red box in the figure. And then for read, you also need to once you notice the data is corrupted, you need to fetch survived data and the parity chunks, and then you can decode them to recover the original data. So now we know how EC works, and also observe that when we use EC schemes in the storage systems, we need to pay the cost of both computation for encoding and decoding, as well as the computation for chunks distribution across nodes, right? So we can say that exploit EC will introduce both computation overhead as well as communication overhead. So this is the cost of using EC, but in the meantime, you gain the storage efficiency. So now the question is, can we make EC run faster so that we can get the both better storage efficiency as well as higher performance? So now the question is, are there any good approaches to improve EC performance? Next slide, please. So before we discuss our approach, let's have a quick overview of the brief history of Erasure coding, such that we know why EC is hot research areas these days and why it has been utilized in the storage systems for years, right? So as we know, in 1950s, Hamming proposed the first Erasure code to ensure reliable communication over unreliable physical channels. So that Hamming code is so famous. I believe many of us all know that, especially for this community. So motivated by the discovery of the Hamming code, many other Erasure codes, such as the Reed-Solomon code we just introduced, and then BCH code and LDBC code have been proposed in the community, in the communication community to achieve transmission reliability. So the successful use of these Erasure codes finally caught the attention of researchers in the storage community as well. For instance, things from 1980s to 2000s, right? We see, RAID technologies have been proposed to ensure the reliability over unreliable storage medium, right? Underneath, actually, many Erasure coding schemes being exploited over there. So in the first decade of the 21st century, because of the fast growth of big data, we see that a lot of distributed storage systems start utilizing Erasure coding schemes to design more efficient code schemes in their systems. For instance, here we can see that there's some solutions called the local reconstruction codes, LRC code, and also the partial parallel repair, PPR, repair pipelining, EC pipe. These codes are also proposed by the data center and the cloud computing and the storage system guys, and they are trying to use them in many different kind of distributed solutions, such as HDFS, Ceph, and the Microsoft Azure storage systems. So because of this code, actually based on this work and also inspired from their work, we propose different solutions in our group as well. We have 3 different kind of designs. One is called UMREC, which is actually trying to use heterogeneous storage heterogeneous devices to concurrently code and decode one chunk in parallel. For instance, we can uniformly run EC schemes on top of GPU, CPU, and SmartNICs, and by a uniform API. That's called UMREC, Uniform Multi-Rail EC. And then in last year, I believe many of you remember, I gave a talk in this forum, which I introduced a novel design called Tri-EC in our group, which means tripartite graph-based EC schemes for SmartNIC offload, right? So compared with the default current solution on SmartNIC EC, our Tri-EC can achieve much better overlapping and parallelism. So this year, I want to introduce a new work we did, just like a follow-up design in our group, which is called INEC, so in-network EC. We want to examine that whether we are able to make our Tri-EC designs more generic and it can support all different kinds of EC schemes, not just the conventional RS code. That's our motivation. Next slide, please. So before we go there, let's briefly take a look what kind of communication or EC operations are there for state-of-the-art EC schemes these days available in the community, right? So here earlier slides we introduced RS code, Tri-EC code, which from my group, and then RS code, PPR, and EC pipe. And if you show them in a graph perspective, then you see that we briefly can try to classify our nodes in these graphs in different kind of categories. So for instance, these highlighted nodes in different EC schemes in the green box need to perform EC computation and then send the results to other nodes. And then for those nodes highlighted in the yellow box, they have to wait for some data first and then conduct EC calculations and then send the results. We also have nodes highlighted in the blue box that need to do some kind of computation on the received data, but don't send the results to the other nodes. So they just wait for the data to arrive and then carry out the computation on top of them. And then there are also some nodes in the red box just need to perform networking functionality such as send and receive. So with all these different state-of-the-art EC schemes, what kind of opportunities and the challenges are there for us to further optimize their performance, right? Uniformly, especially. So next slide, please. So now let's take a look what kind of opportunities and the challenges are there. Next slide. So after reviewing the state-of-the-art EC schemes, we know that EC calculations are in tight conjunction with networking functionality. Therefore, we believe that EC-capable SmartNICs, these days available in data centers and HPC clusters, which are commonly used in many systems, are promising for designing next-generation storage systems. I believe this will be particularly interesting for this community. That's why I choose to present this work in this forum as usual. Next slide, please. So typically, some of you who may not be familiar about the modern SmartNIC's capability of EC support, let me use these slides to introduce what existing solutions are there, right? So broadly, we can classify the EC capabilities on modern SmartNICs into two different kind of categories. One is called incoherent EC calculation and networking. The other one is called the coherent EC calculation and networking. So for incoherent approach, CPU needs to talk with SmartNIC for many times to complete EC computation and data transmission. So for coherent approach, we also call the coherent network EC in this work. So with this approach, CPU can offload the EC computation and the communication tasks to SmartNIC with one post, so that the SmartNIC will automatically execute these tasks one by one without any further CPU involvement. So with this approach, we can see that there's a potential to reduce the DMA traffic as well as reduce the CPU involvement, and then which can further improve system performance. Next slide, please. So another question is, how can we support different kind of EC schemes we interested in the earlier slides, right? There's many different kind of graphs available for those EC schemes. Another question is whether we can use coherent in-network EC concept to uniformly support them, and what kind of challenges to design new EC schemes on top of SmartNICs or high-performance networks. So first of all, of course, what should be the primitives, right? We can effectively support existing different kind of EC protocols or schemes. And how can we make EC calculations and networking functionality coherent for all the proposed coherent in-network EC primitives? And then what kind of performance benefits, how we can verify whether they're correct, and also how we can verify the efficiencies of our proposed designs. These are the three major challenges and the questions we are going to answer in the rest of slides. Next slide, please. Okay, so our work called INEC, coherent in-network EC primitives. Next one, please. So this table actually is trying to summarize a set of coherent EC primitives we proposed, and which includes three types of essential primitives. It exposes a set of flexible APIs to upper layer applications, such that users can specify various parameters to meet their needs. So for instance, our API is pretty flexible. You can indicate what kind of calculator you want to run in our API, and what's your communication channels, memory layout, as well as number of receives you are going to wait for. So essentially, you just have to invoke INEC EC send, INEC receive EC send, and INEC receive EC, these three different kind of APIs to implement different kind of EC schemes we discussed earlier. So next slide. So the first primitive in EC is called EC send. After receiving the EC send request from CPU, INEC fetches data chunks from the host memory and puts the data chunks into the INEC buffer, and then performs EC or XOR computation on these data chunks, and then finally sends out the computation results to other nodes in the cluster. So with the EC send primitive, we are able to reduce the amount of CPU involvement and DMA traffic. Next one, please. So the second primitive is called receive EC send. Once CPU issue one receive EC send request, INEC starts to wait for node chunks. And then once the remote chunks arrive, INEC ships or relate data chunks from host memory to INEC buffer file DMA operations. And then it performs EC XOR operation on the local chunks and the received chunks. Finally, INEC sends the computation results to other nodes. With receive EC send, we can reduce the number of CPU involvement and the DMA operations as well. Next slide. So then the third primitives we propose is called the receive EC. So once CPU reissues receive EC, so INEC will start to wait for remote chunks. And once the remote chunks arrive, INEC fetches or relate data chunks from host memory and puts them on the buffer, on the INEC buffer. And then after data placement, INEC performs EC or XOR operations on the local chunks and the received chunks, and also put the computation results into host memory. So using the receive EC primitive, we can further reduce the amount of CPU involvement. The next slide, please. Of course, now the question is, if we just have primitives, it's still hard to use, right? Because it's too low level. So you need some kind of abstraction to help to design some kind of graphs for different kind of EC protocols. So now towards flexibly integrating EEC primitives into EC schemes, introduce an abstraction called dynamic EC graph, like you can also call it DEC. So this abstraction is used to construct EC schemes and automatically apply EC primitives. So this essentially is a directed cyclic graph. So the basic rules for automatically applying EEC primitives are first, all vertices in this graph with 0 in degree choose to use EC send API. And then second, vertices with 0 out degree can use receive EC, and the other vertices in between can leverage the API we proposed, like a receive EC send. And all vertices are with an explicitly specified computation type such that they can choose proper calculators to carry out different kind of computations in the runtime. So next slide. So all these primitives analysis and performance models we have introduced in our paper, which published in SE 2020. So if you're interested, you can take a look at the details. And we implemented our code inside the manlogs of FedDriver 4.7. And we also try to show this is useful and very efficient. We co-designed our prototype with memory cache D. We call it INEC cache. So this is the figure how we can design a real key value store for data centers, right? So this is for more details, please feel free to get more information from our paper. Next slide, please. Because of time, we can not introduce all kind of details. So now let's take a look for the results and what kind of benefit we can achieve with our proposed INEC primitives in the network. Next slide, please. So these slides show 3 different kind of EC schemes we have shown earlier. One is conventional RS code, and then one is ARC code, and one is tri-EC code we proposed last year. So as you can see that we compare different kind of configurations for ECs, like 3,2, 6,3, 12,4, or 422, 622, 1222, some different kind of way you can configure your EC protocols. So as we can see in all these figures, the encoding latency of RS code can be reduced by 2.28 times by using our INEC primitives, okay? And then the encoding latency of ARC code is also reduced by 1.58 times, as shown in this figure, but up to, okay? So for tri-EC code, we can see that the INEC improves performance by up to 3.3 times, and since the primitives used in INEC are able to reduce DMA traffic, so and also we see that INEC presents performance improvement even for large data chunks with tri-EC code. Next slide, please. And for latency, now let's take a look at the bandwidth. So in the encoding bandwidth evaluation, INEC improves bandwidth of RS code by up to 2.7 times, ARS code by 2.6 times, and the tri-EC code by 5.8 times, okay? Also note that tri-EC with INEC primitives, basically last year work and this year work, if we combine them together, we are able to achieve the best bandwidth performance among all the different kind of EC schemes available. Next one, please. So now let's take a look at the decoding performance. So here, first 2 set of results is for RS code and the EC pipe. So this is for decoding latency. As we can see that our proposed approach can reduce the decoding latency for RS code by up to 54%. And then the decoding latency benchmark for EC pipe code shows that INEC improves performance for all chunk sizes and achieves a performance boost of up to 72%. So INEC performs better for all chunk size because of the 2 key contributions of our designs. First of all, like the primitives used in EC pipe involves trivial overhead and therefore delivers performance gains. And secondly, both primitives are able to reduce DMA traffic, which further boosts performance as well. So next slide, please. So this slide further show different other 3 different kind of codes in terms of their decoding latency. Okay, ARC code, PPR code, and tri-EC code. As you can see that for small chunk size INEC in ARC code incurs a little bit performance degradation. This is mainly because of we need to store some kind of states in the NIC. But if you look at the latencies for ARC, PPR, and TriEC. We for other data sizes, we can achieve up to 57%, 51%, 64% different kind of performance benefits respectively. Next slide, please. Now we can also take a look at the bandwidth performance as well for decoding. So here we can see that for decoding bandwidth, INEC improves bandwidth performance for all evaluated EC schemes. And you can see that ARC, PPR, EC pipe, and the TriEC can be accelerated by INEC primitives by more than up to 2 times in terms of peak bandwidth. Okay. So here interestingly see that ARC code performs the best for bandwidth. This is mainly because ARC code incorporates some kind of local parities so that you can get a better performance. Okay, that's the main reason. Next one slide. Next slide, please. So for data center workloads, many of us actually are interested with not only for average latency and the bandwidth, we're also interested with the tail latency problems, right? So here we actually trying to show that we choose a set of figures from our paper to show how INEC impact on percentile latencies. Please refer to our paper for more numbers and figures. And then the latency distribution in these figures demonstrate that INEC can alleviate the performance fluctuation introduced by frequent context switches and compared with baseline. INEC reduce like 50s, 95s, 99s percentile latency by up to 77%, 66%, and 62% respectively. So the figure A in this slide show that if you have node filter, how the deck looks like. Okay, so in our paper we actually show different kind of filter cases for different schemes, so we can support all of this kind of node filter recovery. Next slide, please. So since earlier we introduced that we can also we can design real key value stores or other distributed store systems with our INEC primitives and the deck, the 5 abstraction we proposed. So here we just want to show that what kind of numbers we can get in INEC cache level. Okay, this means almost like application level performance. Okay, so we use YSSB workloads. We use workload A, B, and C to evaluate our performance. So this is the end throughput numbers with respective to the baseline compared with baseline. Okay, so this shows the ratio in these bars. So we can see that INEC presented an average performance boost up to 57% with read-dominated workloads, and average performance speed up about 28% with write-heavy workloads. Next slide, please. Okay, so with this, let me conclude my talk and show what kind of impact we are going to deliver to the community. Next one, please. So I think we have some strong impact of this work to the networking community. Okay, first of all, our proposed designs are generic and abstract, such that they can be applied to different kinds of distributed storage systems as well as EC schemes, as we have seen in our numbers, right? So far, we choose 5 different kind of EC protocols or EC schemes to be implemented in our system. So we believe that other EC schemes can be supported in the same way as well. The secondly, we find that our design improves the efficiency, parallelism, overlapping, and so that you can deliver better performance for upper level applications, so that we can make EC become more viable for designing next generation storage systems. So the third impact we think we have is we propose efficient, coherently network EC primitives and the TriEC paradigm. So we believe that these designs can be integrated into next generation smart NICs drivers. So just like we did with Mellog's OFED. So we believe for other vendors we can do similar things. If you have interested, we can talk and for more collaborations. So if you have more interest in our work, feel free to send me email or take a look at our paper in SC20 as this reference shows. With this, thank you so much. Next slide, please. So this end of my talk.
Any questions for Xiaoyi? There was one that came through the chat while people get prepared. I'll bring it up. So this INEC method of achieving data reliability, are there any real world applications that is using this approach? Anything you can talk about in terms of applications, and what have you seen in the product landscape?
Okay, so you're talking about EC or you're talking about my design, specifically my design. If you're talking about
Actually, both. I think let's talk generally and then about your design.
okay. If generally, of course, there are a lot of application, a lot of systems in cloud already use EC skins like Ceph, HTFS, right? And the Microsoft Azure, they already have the ARC. I think the ARC or they are like just one of the EC skins I discussed in my talk is actually proposed by Microsoft Azure team. So it's already widely used in the storage backend. So this is not something new, right? So so our contribution is we are trying to make all these EC skins can be offloaded efficiently and effectively on NIC. That's our contribution. Okay. Earlier design typically they are either implemented with CPU, GPU, or on the storage controller. But we say that okay, for distributed EC skins, you already need to involve network heavily, right? Then why not just combine with smart NICs so that we can do that on smart NIC efficiently, so that you don't have to use those kind of devices or solutions. That's our major goal. And regarding who is using our solution, so our solution just become available since last year and this year. So of course, we are happy if some companies want to collaborate with us, we're happy to work with you guys, open source code, whatever. But of course, we can discuss more.
Okay, thank you, Xiaoyi. Any other questions for our speaker here? We have a very quiet audience today. Okay. All right. So then thank you for taking the time to speak with us today, and we will go to our next session now.
Sure. Thank you.